Look at the Earth from space. Blue ocean, white cloud, brown land, a thin atmosphere wrapped around a moving planet. From this distance, water seems to be everywhere and nowhere at once. It fills the basins between continents. It hangs in the air as vapor and cloud. It freezes into glaciers and snow. It occupies the pores of soil and rock, flows through rivers, enters plants, passes through living bodies, and returns again to the air, the land, and the sea. But the water you see is not a single lake with one simple route. It is a planetary network of storage places and transfers. A pool is a place or state in which water is held. A flux is a process that moves water from one pool to another. The ocean is a pool. A cloud is a pool. A river is a pool in motion. Evaporation is a flux. Rain is a flux. Infiltration is a flux. This distinction is the first key to the atlas. Water is not only a substance, it is a traveler between systems, and every system gives it a different speed, temperature, chemistry, and opportunity to move again. Today, we follow the first map of that journey. We will not try to explain every pump, pipe, microbe, or membrane yet. We will build the foundation: where water is stored, how it changes state, what forces it to move, and how human beings add a new layer to the natural cycle.
The largest visible store of water is the ocean. It is saline, and it is connected to every other part of the cycle through the atmosphere, the surface, and the ground. On land, water can be stored in lakes, reservoirs, wetlands, rivers, soil moisture, snow, and ice. Below the surface, it occupies fractures and connected pores in rock. The upper boundary of the saturated zone may form a water table. Deeper formations that can transmit enough water to wells and springs are called aquifers. The atmosphere stores water too, even when the sky looks clear. Invisible vapor can be carried over long distances before it condenses. Plants store water temporarily in tissues, then return much of it to the atmosphere through transpiration. Animals and people also become short-lived pools in the cycle. A glass of water, a reservoir behind a dam, a wetland, and a cloud are very different in size and chemistry, but each can be represented on the same atlas, a storage place connected to other places by fluxes. Some storage is easy to see, some is hidden. A river can be full on the surface, while its surrounding sediments quietly exchange water below. A dry landscape can still contain a deep aquifer. A city can appear to have no river at all, while thousands of kilometers of pipes move water beneath its streets. To understand water availability, we must ask three questions together. How much water is stored? When will it move? And how clean will it be when it arrives? The answer changes from one basin to the next. A mountain catchment, a coastal plain, a desert aquifer, and a crowded city do not keep water in the same way. The cycle is global, but water decisions are made in places.
Now the atlas begins to move. When liquid water receives energy at a surface, some molecules escape into the air as vapor. This is evaporation. Water released by plant leaves is transpiration. Together, evaporation and transpiration form one of the main pathways by which water enters the atmosphere from the land and the ocean. Higher in the air, vapor can cool and condense into liquid droplets or ice crystals. Clouds are not a single solid object. They are changing populations of droplets and crystals suspended in moving air. When water returns to the surface as rain, snow, sleet, or hail, we call the transfer precipitation. Some water lands on leaves and evaporates again. Some reaches the ground and flows downhill. Some enters the soil. Some become snowpack or ice. Some is taken up by roots. Water that moves across the land surface is runoff. Water that moves through a channel is streamflow. Water that enters the soil is infiltration. Water that continues downward through the soil toward the saturated zone is often described as percolation. Once below the water table, it becomes part of groundwater flow. Groundwater may later emerge at a spring, feed a river, discharge to a wetland, or move toward the coast. These words are not labels for separate worlds. They are names for connected transfers. The same molecule can evaporate from the ocean, condense in a cloud, fall as rain, infiltrate into soil, move through an aquifer, enter a spring, flow down a river, and return to the sea. It may also enter a city, pass through a treatment plant, irrigate a field, or be reused by an industry before it reaches the coast.
The water cycle has no engine room with one machine. It is powered by several forces acting together. Solar energy warms surfaces and supplies the energy needed for evaporation and evapotranspiration. Gravity pulls precipitation downward and drives much of the flow across slopes, through channels, and into the ground. Wind transports moisture through the atmosphere. Temperature controls whether water is more likely to remain liquid, become vapor, freeze, melt, or condense. Terrain directs surface water. Rock and soil decide how easily water can enter, be stored, or move underground. A useful model is a balance. For any selected area, the change in stored water depends on what enters and what leaves. Rain, snowmelt, river inflow, groundwater inflow, and managed supply may add water. Evaporation, plant water use, river outflow, groundwater discharge, pumping, and human consumption may remove water from that selected store. The exact balance depends on the boundary and the time period. A basin measured over one day is not the same system as a continent measured over a century. That is why a single arrow labeled water cycle can be misleading. It hides differences in speed and direction. A cloud can cross a country in hours. A river can reach the sea in days or months. Water in an aquifer may move much more slowly, depending on the rock and the hydraulic gradient. Ice can store water across seasons or much longer. The cycle is continuous, but it is not uniform.
Imagine a drop arriving over a mountain catchment. It touches a leaf. Part of it slides to the ground. Part of it is intercepted, held briefly, and returned to the air. On the soil, the drop faces several futures. If the surface is already saturated, steep, or covered by an impermeable road, it may join runoff. If the soil has open pores and the rainfall is gentle enough, it may infiltrate. Roots may take it up. The sun may return it to the atmosphere. It may percolate deeper and recharge an aquifer. If the drop enters a stream, it begins a visible journey. The channel gathers water from hillsides, springs, tributaries, and sometimes storm drains. The water carries sediment, dissolved minerals, organic matter, and whatever the landscape has allowed to enter. The river is both a pathway and a changing chemical environment. If the drop enters an aquifer, its journey becomes hidden. It may move between grains of sand, through fractures, or along layers of rock with different permeability. A well can intercept that flow, but the well does not create the water. It draws from a connected storage system whose replenishment may be faster or slower than the pumping rate. At the coast, the drop may return to the ocean, but the human story can interrupt the natural route long before then. A city may capture the river. A reservoir may store it. A treatment plant may remove suspended particles and reduce pathogens. A home may use it for drinking, washing, or sanitation. A farm may apply it to crops. A factory may use it for cooling or processing. The used water may enter a sewer, a treatment plant, a reclaimed water system, a wetland, a river, or a managed aquifer recharge project.
The water cycle is also a clock, but it has many hands. Some transfers are rapid. Others are slow enough to be invisible within a human lifetime. A storm can transform a dry channel in minutes. A reservoir can store seasonal water for months. Snow can delay a mountain supply until spring. Soil moisture can disappear between two weather systems. Groundwater can sustain a stream during a dry season, while an aquifer under pressure may preserve water far from the place where it entered. This difference matters because water can be abundant in total and still unavailable at the time or place people need it. It can be present, but too salty, too contaminated, too deep, too frozen, or too expensive to move and treat. Availability is therefore a combination of quantity, timing, location, and quality. Human infrastructure changes the clock. A dam changes when river water moves downstream. A well changes the local pressure and storage of an aquifer. A paved surface changes how quickly rain becomes runoff. A treatment plant can shorten a route by turning used water into a new supply. But that shortcut still requires energy, monitoring, maintenance, and a safe end use.
Now we add the layer that makes the modern water cycle an engineered system. People withdraw water from rivers, lakes, reservoirs, aquifers, and other sources. They use it for public supply, homes, irrigation, industry, energy, mining, livestock, and aquaculture. Some of the withdrawn water returns to rivers or groundwater. Some evaporates, becomes part of a crop or product, or leaves the local system as consumptive use. Cities separate, connect, and redirect flows. Drinking water networks bring treated water toward homes and institutions. Sewer networks collect used water and transport it to treatment. Stormwater systems carry rainfall from roofs and streets. In some places, these flows are separated. In others, they can meet during storms. Industrial water may require pre-treatment before it enters a municipal system. Every connection creates a benefit, a responsibility, and a risk that must be measured. The next episodes will enter these systems one by one. We will go from the river to the intake, through the treatment train, along the distribution network, into the household and factory, down into the sewer, through biological reactors and advanced membranes, and back to the basin. The natural cycle and the urban cycle will no longer appear as separate stories. They will become one connected map.
At the end of this first map, the water is still at the ocean's surface. Sunlight is arriving. The sea is moving. At the boundary between liquid water and air, molecules are exchanging places every moment. Some return, some remain. Some escape upward and begin a new atmospheric journey. In the next episode, we will slow down to watch that departure. We will follow evaporation, plant transpiration, heat, wind, and humidity as the ocean breathes water into the sky. There is no final drop. There is only the next transfer.
A map of water is incomplete if it shows only blue lines and volumes. Water also carries a history of contact. As it moves through air, soil, rock, cities, farms, and factories, it can acquire dissolved minerals, suspended sediment, nutrients, organic matter, microbes, heat, or manufactured chemicals. Some of these are natural. Some are added by human activity. Some are harmless at one concentration and harmful at another. Some remain attached to particles. Others travel invisibly in solution. This is why the next question after where is the water is what is in it and what must happen before the next use. A river may be suitable for an ecosystem but require treatment for drinking. Groundwater may be naturally clear but contain dissolved constituents that need control. Water that has been treated for one industrial purpose may not be suitable for irrigation or human contact. Safety is not a color on the screen. It is a chain of evidence, treatment, monitoring, and appropriate use. The atlas will keep these two dimensions together, quantity and quality. A healthy basin needs both water that is present and water that can safely serve its intended purpose.
In the chapters ahead, every pump, basin, filter, reactor, membrane, and discharge point will be shown as part of that combined question.